Okay, so we're going to talk about something called Dalton's law of partial pressures, which really should be called Dalton's law of mixtures of gases. The first part of Dalton's law of partial pressures is pretty simple, and it has to do with gases being added together. It says that if you have individual gases, so we have some red gas here, there are 3 particles, and it's at a pressure of 1, we'll say atmosphere, and we're adding that to some blue gas, which is at a pressure of 3 atmospheres, and there's 1, 2, 3, 4, 5, 6, 7, 8, 9 particles there, and we add that to some green gas, which is at a pressure of 2, and there are 6 particles here. If we add those together, the pressures are additive. So the pressures are additive. So 1 plus 3 plus 2 is equal to 6. And also, the moles is additive. Okay? So if we add those up, there should be 18. And that's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18. There are 18 in that container. So pressures, so pressure 1 plus pressure 2 plus pressure 3, and this could be true for as many gases as we had, would be equal to the total pressure. And then the moles is also additive. When we think about that, it usually makes sense to people that if you add things together, what you get at the end is just those things added together. But we just want to make sure that we're putting the equations in the right way. So we can add pressures together to get a total pressure, and we can add moles together to get a total moles. This doesn't actually work with gases if you try and add volumes together, because there's so much empty space in a gas that when you add 2 volumes of gases together, you can actually get them to add up. If you put them in a different container, you can get them to add up to actually a smaller container. So total volumes don't work with gases just because they're so compressible. Right, if you want to hear this in a different way, this is how Dalton said it. He said that the total pressures exerted by a gas mixture, so that's the total, is the sum of the partial pressures of the components of the mixture. So what he's saying is that the total is equal to the pressure that one gas exerts, and we call that a partial pressure. So this would be the partial pressure of gas 1, and then this would be the partial pressure of gas 2. So partial pressures are just the individual gases. The total pressure is what they all add up to be. Now let's think about how this applies to our ideal gas law. If I write it here like this, I'm going to just manipulate this around so that pressure is on one side. So that would be pressure, so pressure is by itself on one side. So it'd be nRT divided by volume. Okay, so just a little algebra there. So the way that this works is that if you put in the total moles, you can calculate the total pressure. And that would apply to a problem where maybe you had something like a mixture of helium, hydrogen, and argon. And if you're trying to find the pressure total, you would have to put in the moles of helium plus the moles of hydrogen plus the moles of argon. So that's the total moles, then RT divided by V. That's how you would do it. What you couldn't do is just put in the moles of helium, or the moles of any of them, and expect to get the total pressure. Because those don't match, you're not going to get what you think you're getting there. So when you're doing these problems, you need to consider whether you're just trying to calculate something for one gas, if you're trying to calculate something like a total for all the gases. If you want the total, you need to put in the total moles. If you just want the pressure of one gas, you would put in just the moles of that one gas. just a little reminder, if you are calculating just the pressure of one gas, we call that the partial pressure of that gas. So in this equation here, I would be using the moles of helium to calculate the partial pressure of helium. Okay, another way that we can look at a mixture of a gas is by looking at this thing called the mole fraction, okay, and it's represented right here. Now, mole fraction is technically a concentration, and you might have learned it when you were learning about concentration in a kind of previous class. Sometimes it's one that's skipped over. So what it means is the moles of one thing divided by total moles. It is unitless, meaning it's not like a percent, it's not like molarity or something like that. It's unitless because moles cancel out. And it is a number between 0 and 1. If the mole fraction is 1, it means that your mixture only has one kind of gas, and it is all of that one thing. If your mole fraction is 0.5, that means that you have a gas that takes up 50% of the moles, or half the moles is another way of saying that. And how this applies to our partial pressures is that we can use a mole fraction to also calculate the partial pressure. And here's the equation here. What that equation is saying is that the partial pressure, so remember, partial pressure just means the pressure of one gas, of gas A, and I know that because of here. So the partial pressure of gas A is equal to the total pressure of all the gases times the mole fraction of A. So if we knew that gas A took up 50% of all the moles, so its mole fraction would be 0.5. If it takes up 50% of the moles, then its partial pressure is going to be 50% of the total. Okay, well, let's do a little practice with these problems. Here's a problem where we have a mixture of gases. Okay, we have some carbon dioxide, and we also have 0.1, that should be 0.1 grams of helium. Some other information that we know their volume, so they share that volume, and we know the temperature, and we know that we need to get that temperature in Kelvin. So we're going to add 273.15 to that. 17, that's 290.15 Kelvin. Okay, let's look at the problem. It says, what are the partial pressures? So we want to find the pressure of carbon dioxide, and we want to find the pressure of helium, and the mole fractions of each one inside the flask. And then we're going to use that information to find the total pressure. All right, if I'm trying to find the partial pressure of carbon dioxide, I'm going to look at what I have in my problem. I have one volume, I have one temperature, I have a mass, I only have one set of conditions. That means that I'm going to use the ideal gas law. And if I'm trying to find the pressure of carbon dioxide gas, I'm going to put in the moles of carbon dioxide gas. So I'm going to rearrange that equation just so that I get pressure on one side. Like this. Okay, so I'm going to put in my moles. Oh, but I was given grams, so I have to convert to moles. To do that, I'm going to use my molar mass. 1 carbon and 2 oxygens add up to be 44.01 grams per mole. So when I did that on my calculator, I got 0.06816 moles. Okay, and for sig figs, this had 3, so I'm going to mark this to 3 right there. Okay, so I'm going to bring that information down here I have my moles to 3 sig figs. I have R. And I have K. I have my temperature. And then I'm going to divide it by the volume. And I'm going to make sure that my units cancel out. Moles and moles, liters and liters, Kelvin and Kelvin. I'm going to get atmospheres out here. And on my calculator, I got 0.8115. For sig figs, this had 3, this has 4, this had, it's 17, so that's the ones place 3. This has 2, so I can only mark it as 2, be 0.82 atmospheres. And that is my pressure for my carbon dioxide. We also call it the partial pressure of carbon dioxide at these conditions. Okay, now just reading the rest of my problem here, I was able to find the partial pressure of carbon dioxide, but I also now need to do that for helium. The problem's going to be, that part of the problem is going to be extremely similar. We're going to go from grams of helium to moles of helium. And then we're going to use the same equation here, but instead of carbon dioxide, it's going to be heliums. Okay, I've written out our equation again here. I need to do my mole conversions, so 0.10 grams of helium. Heliums are 4 grams per mole, and so I got 0.025 moles for this. When I put that in, and the temperature is the same, and the volume is the same. On my calculator, I got 0.2976. I'm still just going to get 2 sig figs, so it's going to be, oh, I'm going to have to round up there, 0.3 liters. So, not liters. My units are, let's see, liters cancels out, Kelvin cancels out, moles, it's atmospheres. Okay, so far I've been able to find the partial pressure of carbon dioxide and helium. I'm going to use those partial pressures now to find the total pressure. The total pressure is just the partial pressures added together. Okay. So I had for my helium and I'm going to use the unrounded number because that's the best way of doing things since I actually have the number here. And I'm going to use the unrounded number for my carbon dioxide gas also. All right, so my unrounded number that I had gotten was 0.8114 something. It was only just 2 sig figs also. When I add those together, I get 1.109. Each one of these has 2 places past a decimal, so I'm going to round it to 2 places past a decimal. Considering 1 digit after, that would be 1.11 atmospheres total. So I've been able to do the partial pressures from the first problem and the total pressure. I do want to go back and find those mole fractions of each one of these. And I'm just going to clean up my screen a little bit to make that happen. Okay, so to find mole fractions, we need to know about the moles of each one. And we've done that in our work over here. So we know the moles of the carbon dioxide and we know the moles of the helium. Okay. The mole fraction of carbon dioxide is going to be the moles of carbon dioxide divided by the total. And the mole fraction of helium should be the moles of helium divided by the total. Now, theoretically, these two numbers, the 2 mole fraction, should add up to be 1. But sometimes they don't add up exactly to 1 just because of sig figs. The same way that maybe sometimes percentages add up to be like 99.99%. Here we might get them to add up to be really close to 0, but because of sig figs, sometimes it's not exact. We might get them to add up exactly to 1, but sometimes because of sig figs, they might not add up exactly to 1. Okay, so something both of these equations have in common is we need to know the total amount of moles. So when I added those up, so the moles of carbon dioxide and the moles of helium, I got 0.09316, like that. Okay, so let's go ahead and put our numbers into our equations here. For the moles of carbon dioxide, it's 0.6816. That was sig figs there. And the total, and that should also just be to, oh sorry, that should actually be to 3 places past the decimal. And when I do that on my calculator, I'm going to get 0.7316, and that should just have 2 sig figs. Okay, I'm going to do the same thing on my helium side. My helium was 0.25 moles. That's 2 sig figs. And this also was just to 3 places past the decimal, so that's 2 sig figs. When I put it in my calculator, I got 0.2683, and we should only have 2 sig figs there. All right. So that's for the carbon dioxide. This is for the helium. Now the last thing I want to check, I just do want to check to make sure that they add up to be about 0.1. That's a good check on these problems and kind of helps you stay in perspective whether, if you have questions, am I even doing this right? If you do this final check and they add up to be 1 at the end, things probably went pretty well. So when I add them together, I got 0.9999. Yeah, so that is really close to 1, and that's just because of sig figs that it didn't come out to be exactly 1 there. I'd like to talk about how Dalton's law applies to kind of some real-world situations. If you haven't thought about it, anytime you're doing a chemistry experiment where you're creating a gas, most of our gases are clear and colorless, and so it's hard to even tell that you're creating a gas because it mixes with the air around it, and we can't tell the difference between them. So usually, when we're creating a gas that we want to collect or we want to monitor, we set up the situation in which we bubble the gas through water, because then we can tell where the gas starts and where the gas stops. It displaces the water, and so we can tell the kind of the volume that the gas is taking up. So we have a picture over here, and I regret that a lot of the picture got kind of cut off, so I'm going to draw in what's missing here, but I'm going to start with the parts that are actually there. Okay, so in this test tube, we have a reaction going on. It's zinc plus hydrochloric acid. That is a single replacement reaction. It makes zinc chloride and hydrogen gas. Like that. Okay, so this hydrogen gas is filling up this container. It's bubbling. You can see there. It's filling, and it's going through this tube. And as it's being created, it's pushing through this tube. And what you can't see, what kind of got cut off here, is that this is a tank of water, like this. And this is a beaker, like this. Okay. We can do that a little bit better. So this is a beaker, like this. Okay, and so this tube is actually going up into this beaker. Now the beaker contained water at the very beginning, so it's like an upside down beaker full of water in a tank of water. And as the gas comes down this tube and goes in, the gas is less dense, so it floats to the top. And the gas starts to take up the top part of the beaker and it pushes the water down into this tank here. Okay, so the water's coming out of the beaker and the water level of the tank is going to go up. Now again, why we would go through all of this is because if we were just to do the test tube with the hydrochloric acid and zinc in it, if we wanted to measure the volume of the gas produced and we just did it in kind of an open test tube, the gas would be lost to the atmosphere, and there's no way that we can collect that gas unless we kind of put it through this tube and collect it in some kind of vessel. Okay, and it's easiest to do it where we call it collecting it over water. That's this situation here where we're bubbling it up through water. It's easiest to collect it this way because we can see where the gas stops. We know the gas stops where the water begins. And so that way we can find the volume of the gas. Now, there's a little problem with this. So this is the inlet of this tube here. And it's not really a problem. It's just something that we have to take into consideration. Anytime you bubble up a gas through water, it actually grabs some of the water on its way up. And so when we say that this volume up here contains just our hydrogen gas, that's not true. It actually contains our hydrogen gas plus some water that it's picked up along the way. So this is a mixture of gases. And we can't stop that from happening. Anytime you bubble a gas through water, it's going to take some of it with it. So this is a mixture of hydrogen and water vapor. And because we have a mixture, now Dalton's law of partial pressures applies to this gas up here in the container. Now the good news is that even though we have a mixture and we have to know about both of these things to be able to do calculations, people have studied water really, really well, okay? And we actually know what the partial pressure of water is at almost every temperature that we will be dealing with. There are tables of these things that you can look up, and they're just called water vapor pressure tables. And there's definitely one in your book. There's also one in your lab manual. And it looks something like this. So it says the vapor pressure of water. And what it does is it has, at different temperatures, somebody has measured the partial pressure of water in torr. Okay, so we have a temperature and its matching pressure. These temperatures and their matching pressures. So it's actually like a dated table, like here, each one of these is a long list of data. So even if you have a mixture with water, the water part is already really well studied. So those are just numbers that we look up, not numbers that we actually have to measure. And that means that we can concentrate on measuring things about the gas that we are actually interested in. So let's do a practice problem like that. Okay. This problem says that we have a volume of hydrogen gas. It was collected over water. Anytime it says that, or it says that the gas is a wet gas, you know you're going to have to subtract out the pressure of water if you want to find just the pressure of your gas. Okay, so we have a gas collected over water at 18 degrees C. The barometric pressure is 500 or 751.2. Barometric pressure is always the total pressure. Okay. What volume would this gas occupy at STP? Ooh, so this seems like it's probably a combined gas law problem. We're changing conditions here. And it says we might need to see the appendix for the water vapor pressure table. That's this table right here. So we'll look back at that when we need to. Okay, so when I read this problem again, realizing that we are going to be changing conditions to STP, that makes me realize I need to keep careful track of my variables here. So I'm going to go back and just kind of mark them. I have an initial volume. I have an initial temperature. I have an initial pressure. And that I'm just going to remind myself is the P total, but it's initial. I'm going to try and find V2. And STP tells me that I'm going to be at 273.15 Kelvin for my temperature 2, and my pressure is going to be, my pressure 2 is going to be 1 atmosphere. All right, so I'm just going to reorganize my stuff off to the side here. So volume 1, 75 milliliters. T1 is 18 degrees C. I'm just going to convert that to Kelvin right now. So that's 291.15 to the ones place. All right, my volume, my pressure total is 571.2 torr. That's equal to the pressure of my hydrogen gas plus the pressure of my water gas. I'm only interested in the pressure of the hydrogen gas. So what I'm going to do here is I'm going to subtract out the vapor pressure of water. So algebraically, to write that, I'm going to say that 751.2 torr minus the pressure of the water is going to be equal to the pressure of the hydrogen. And that's what I want. Okay, so I need to be able to look up that partial pressure or the vapor pressure of water at the temperature. So I'm going to look at my temperature here. It's 18 degrees, and I'm going to go back to that table. Okay, this is going to be hard. Oh, you guys. So at 18 degrees, this starts at 19.1. So we're not going to be able to use this table. I'm going to have to look up the partial pressure of water for us at 18 degrees. Okay, so algebraically, if I was going to write this out, I would say that 751.2 torr minus the vapor pressure of water is the pressure of my hydrogen. And that pressure of my hydrogen is what I need to be able to do my problem, because that's what I need to put in an initial condition, and I want to get out a final volume. So I just want the final volume of the hydrogen gas, so I need to have the partial pressure of the hydrogen gas. That means that I need to be able to find this number. I need to be able to look that up. We would look that up on a table, so a vapor pressure of water table. I'm just going to go back to this slide, and we would look it up here, but this table starts at 19.1 degrees, so we're not going to be able to use this table. I had to look up the partial pressure of water at 18 degrees. I found that it was 15.5 torr. So if I put that in, I can get the partial pressure of hydrogen. When I do that, I get 735.7. So that's the pressure of my hydrogen. Okay, so I have my initial volume, I have my initial temperature, I have my initial pressure. My final temperature is going to be 273.15. My final pressure is going to be 1 atmosphere. Okay, so my next step is to find an equation that has all the things that I need. I need something with volumes, temperatures, and pressures in it. And if I use the combined gas law, that would be P1 V1 over T1 equals P2 V2 over T2. And I am trying to find my volume, so I'm going to rearrange this so that volume is by itself on one side. That means multiplying both sides by T2, so those cancel out, and I'd get T2 P1 V1 T1 2, and then I'm going to divide both sides by P2, so those would cancel out. And what I'm left with is T2, P1, V1, P2, T1, volume 2. Okay, so I can start putting these into my variables into my equation. I'm going to start with T2. My T2 was 273.15 Kelvin. Pressure 1 is the pressure of my hydrogen gas, which is 735.7 millimeters mercury. My volume one was 75 milliliters. On the bottom, I have P2, which is 1 atmosphere. Uh-oh. So I'm looking at this, and I'm seeing that my pressure units up here and my pressure units down here are not going to cancel out. Okay, so I have to change both of them into millimeters of mercury or both of them into atmospheres. I'm going to choose to take my, put my atmospheres into millimeters of mercury because I know that 1 atmosphere is 760 millimeters of mercury. So that's an easy one for me to do in my head. And if this has 3 sig figs, that's going to have 3 sig figs. But at STP, it's a defined condition, so it's actually like an infinite number of sig figs. So I'm just going to give myself another one there, just so that it's not going to be the limiting one. All right, so that's 1 atmosphere in millimeters of mercury. Okay, the next thing that I need is my temperature one, which was 291.15 in there. Okay, so when I did this on my calculator, I got 68.11, and my units are going to be, let's see, the kelvins canceled out, millimeters of mercury, milliliters. For sig figs, this had 4, this had 3, 291 only had 3, this has like an infinite because it's defined. So that it probably has infinite too. Okay, so 3 looks like. So this would be 68.1 milliliters would be the volume of my hydrogen gas. Okay, if I'm thinking about, like, does that answer make sense? It wasn't that much different than my original volume, okay? I was thinking about what happened in the problem. My temperature went down a little bit. It went from 18 degrees Celsius to essentially 0 degrees Celsius. But the pressure went up just a little bit. And so those are competing interests there. If the temperature goes down, the volume's going to go down. But if the pressure goes up, I guess the volume would also go down a little bit. So it makes sense to me that it went from 75 milliliters down to 68 milliliters. Okay. What I'd like to do is I'd just like to clean up my screen a little bit and then just kind of review the process that we did here. Okay. Ooh, so clean. All right. So the first thing that we did is when we were reading the problem, we recognized that it said that it was a wet gas. Okay. So we wrote down our variables. So we wrote down the volume, the temperature, things like that. We made sure that we took that it was a wet gas, or that it was collected over gas, into consideration. Okay, that means subtracting the vapor pressure of water from the total. Okay. Then we decided on which equation to use. We made sure that our units worked. And then we solved just by putting in our variables into the equation that we had decided on. I want to put an exclamation because the solve part always feels very satisfying. All right, that's our video on Dalton's law of partial pressures. And it's really just about mixtures of gases. We learned how to calculate the mole fraction. We learned how to calculate partial pressures and total pressures. And we learned how to take a wet gas which is a gas collected over water, into consideration by subtracting out the vapor pressure of water. And we did a practice problem. If you'd like some practice doing some Dalton's Law problems, if you go to your course pack and Gas Law Practice 3, which is on page 49, it would be number 4, 5, and 6.